All right, let's see an example or two of decision trees in action. Now, before we can actually do that, we need to install a package called pi.plus that will allow us to visualize these decision trees and make pretty flowcharts out of them. So if you're still in Jupyter Notebook, I need you to quit out of it and quit your Anaconda prompt as well. And now go back into your Anaconda prompt. So go to Anaconda 3, Anaconda prompt. We're going to be installing stuff, so to be safe, right-click on that, go to More, and say Run as Administrator if you're on Windows. All right, let's cd into our course materials directory before we forget. And we want to do conda install pi.plus, just like that. Let that run for a minute or two. Okay, that was pretty straightforward. It just had to install that one package. So now let's start our notebook. Jupyter Notebook. And go into section 7 and open up decisiontree.ipynb. And here we go. So we already took care of installing pi.plus. A little bit of a reminder there for people looking at this later on. So let's go ahead and look at that example from our slides. We're actually trying to create a decision tree based on hiring data. So we'll start with that one, a little bit of a fabricated data that's not related to self-driving cars, but again, you don't really see these used too often with self-driving cars. It's more of a machine learning fundamental sort of a thing. We'll get to some more direct applications later. Let's start by importing what we need. We'll import NumPy, Pandas, and sklearn, specifically the tree package from sklearn. That will be our decision tree package. And we will open up from my website the pasthires.csv file, which contains the same data that we looked at in the slides. So let's read that using Pandas and take a look at the first 5 entries. So here we have the raw data here, and we have, as we talked about, years experienced, employed, previous employers, level of education, whether they went to a top-tier school, whether they did an internship, and whether or not they were hired in the end. So here's an example of where you need to clean your data before you actually feed it into a model. A lot of times, a lot of the work you deal with in the world of machine learning is not so much running cool algorithms and developing cool algorithms, it's actually preparing your data to work best with your algorithms. So algorithms tend to be based on math, and math tends to like numbers, right? So the first thing we need to do is convert these y's and n's into zeros and ones, and these BS's and MS and PhDs into ordinal values that represent some level of education in a numerical sense. So let's take care of that, shall we? We can use Pandas to make that pretty easy. So they have a map function in Pandas that lets us very quickly use this little function here that says y is going to be mapped to a 1 and n is going to be mapped to a 0. So we can just transform the hired column into the hired column mapped using that dictionary that maps entries into other values. And we'll do the same thing using the employed field, top tier school, interned, okay? So it's going to apply that same dictionary that maps y's to 1s and n's to 0s to all of these yes or no columns to convert those to binary 0 or 1 values instead. For the level of education, same trick, except we're mapping degree names to numbers. And there is an actual ordinal relationship here where we can say a bachelor's degree is a 0, a master's degree is a 1, and a PhD is a 2. So we'll map that to the level of education column and then look at our transform data frame here. Cool, so it worked. You can see that our y's and n's have all been converted to 1s and 0s, and our level of educations have been all converted to the values 0, 1, or 2, depending on the degree attained. All right. Next thing we need to do is separate out the feature data from the label data. So we want to make sure we can withhold that training label data that we have there and actually test it independently. Now the thing that we're trying to predict is the hired column, right? So we want to extract that hired column and put it off on its own. So our features data will be everything up to that column. That turns out to be column number 6. So if we do a list of df.columns:6, let's see what's going on here. So df.columns, remember, is the column names from our data frame. We're going to pluck out the first 6 column names there and construct a list out of them and then print that out. So what we end up with is a list of all the feature columns, which is basically everything up to the hired column, but not including hired. So we get back those column labels of years experienced, employed, previous employers, level of education, top tier school, and interned. Those are all of our feature attributes that we're going to use to train our system with. Now we can actually construct our decision tree. In this case, our label data is going to be the hired column from our data, and we can construct our feature data frame from just that feature column list as well. So by saying df features, that's constructing a data frame that consists of only these column names that we specified. So all we're doing here is splitting out our data frame into feature data and label data. We then construct a decision tree classifier just using the tree package that came out of scikit-learn. Again, one line of code there to do that. And then we'll train it using our complete data set, all of the feature data and all the label data that we have. Let's go ahead and run that. Hey, that was pretty quick. And now we can display it. So since we installed py.plus, we can actually visualize this thing. I don't want to get into the guts of how GraphViz and py.plus works and whatnot, but let's just run it and see what comes out. And there we have it. So that's pretty cool. So you can see it's pretty straightforward to read this thing. We can see here that if interned is less than or equal to 0.5. Now remember, interned is a 0 or 1 field. So basically, if interned is less than 0.5, that means interned is false. So if interned is false, then it's a little bit a backward way of thinking about it. But basically, if you did not do an internship, that means this will be true. Okay, so we would go down that path. But if you did do an internship, the intern field would be 1. This test of interned is less than 0.5 would be false, and we'd go down this path here. So it doesn't always construct a graph in the most easy to read format, but if you think about it a little bit, it makes sense. What we're saying here is that if you did do an internship, every data point in our training data set said that you got hired. So we just end up getting into this world here where every one of the data points that we have that falls into this category was either one thing or the other. So in this case, everybody was hired. There were 5 samples in our data set that had people that had internships. All 5 of them were hired. We're done. That's what this means. Otherwise, we have to look a little bit more deeply. Were they currently employed? If they are currently employed, again, our data says that we have 3 samples where every single one of them, if they did not do an internship but they currently have a job, all 3 of those people got hired and we're done. Otherwise, we can look further at their prior experience, and it turns out that anything less than 0.5 tends to be the make or break point. If they have any experience whatsoever, it turns out that we would hire them at that stage. Otherwise, we keep on moving down and we look at whether they went to a top-tier school. That turns out to be our final criterion, where we choose hired or not hired based on whether or not they went to a good school or not at the end of the day. So there we have it. Kind of fun to look at though, isn't it? You know, we kind of automatically created this decision tree out of one line of code by giving it our training data. And out came this picture that we can use to make decisions with. Pretty cool. Let's take a look at random forests while we're at it as well. And again, this is a way to try to prevent overfitting by introducing some randomization into how each tree is built. So let's actually create a random forest classifier. This comes out of the sklearn.ensemble package. And we can say we want 10 estimators, meaning that we're going to build a forest of 10 randomly generated decision trees where we're withholding data and randomizing how things are sampled to try to get 10 different takes on how to actually fit a decision tree to the data that we have. So we will fit that random forest classifier given our entire data set of feature data and label data, and we'll make some predictions with it. So let's see if we have a hiring decision or not for a couple of different personas here. We can pass an array of training feature data here for an individual here. We'll say CLF, this is our random forest model, and we'll ask it to make a prediction for the following person here. And this person represents somebody who has 10 years of experience and was previously employed. And we have an unemployed person who has 10 years of experience as well. So let's see what we come up with. Turns out for our random forest model here, we decided to hire the first person, but not hire the second person based on our randomly generated model. So pretty interesting results. And you can actually get different results from run to run here. It turns out that randomness does actually introduce an interesting amount of variation in how these models are built. All right, let's go to a more relevant example based on self-driving cars here. So remember back in logistic regression, we fabricated some data set that said, should I be traveling fast or slow based on how far I am to a bump and how big that bump is. So this is the same exact code from the logistic regression example that we used to fabricate that test data. Let's go ahead and run that. And now we can create a decision tree trained based on that data that we created at random. And let's see what it looks like. So again, we're trying to create a decision tree that will decide whether your car should go fast or slow just based on your distance to the bump and the size of the bump. You would think that would be a pretty straightforward thing to do, right? But holy cow, look at that. Look at the complexity of that decision tree. It's huge. I can't even fit it on one page. So remember we said that decision trees are prone to overfitting. This is basically a textbook example of that. So given the very simple relationship that's inherent in the data, go slower when you get close to a big bump, it's that simple, this is a way overcomplicated approach to making that decision. So this is a good example of overfitting. And it's also a good example of why decision trees are often not the right solution to a problem. They're good for a very specific kind of problem, but this isn't it. Let's go ahead and plot the categorizations that a decision tree model makes. So in the same way that we visualized our logistic regression example by classifying every point on our graph and overlaying the actual training data on top of it, let's do the same thing here using our decision tree model. And yeah, you can see it's definitely overfitting. We have all these weird shapes and little individual rectangles happening here that are just trying to overfit the data and trying to look at individual data points and if you will, not seeing the forest for the trees. Sorry, I had to use that metaphor here. We're talking about random forests, aren't we? And indeed, maybe using a random forest would produce a better result. If you do want a little bit of an exercise here, you might want to try that. See if you can actually get less overfitting with a random forest. But fundamentally, a decision tree probably isn't the right algorithm for this problem. Anyway, let's take a look at cross-validation just to confirm our suspicions that we are overfitting. We can use cross-val score as we did before to actually do 5-fold cross-validation on our decision tree here that's fitted to our bump size versus distance model. And you can see that these aren't very inspiring accuracy values. We actually did much better with logistic regression, where we had an 84% result as opposed to only 77% from decision trees. So you don't have to eyeball it and use your judgment. You can quantify that this model is not the right one for this data. Logistic regression, which is much simpler, is doing a much better job at modeling this relationship than decision trees did. Hey, let's just actually try out random forests while we're thinking about it. Does that actually do any better? Again, random forests are meant to try to prevent overfitting. Let's see if we can actually overcome this problem by using random forests. And we'll use 10 trees in our forest here and evaluate it in exactly the same way as we did before. And yeah, it helped a little bit. We got up to 80.8%, call it 81%, but it's still not as good as logistic regression, which got us 84%. So even using every trick that we have at our disposal to prevent overfitting with decision trees with random forests, it's still not as good as the simpler logistic regression model. So again, decision trees, they're fun to work with, they're fun to look at, and they are useful for some applications. Also important for you to know about as a researcher in machine learning, but for this particular problem, for self-driving cars, not the best tool for the job. Anyway, if you do want to dive in deeper, here's a little bit of a challenge for you. Try to go back to the first activity there based on hiring data and create an alternate, mirror universe where I hire everybody that I normally wouldn't have hired and vice versa. So flip all of those hiring data points around where all of my ones become zeros and zeros become ones for making hiring decisions and compare that decision tree to the one that we ended up with. And it'll just be fun to see how those different decision points change when you actually flip that training data around. So if you want to get more of a hands-on, intuitive feel instead of just running the code that you're given, that's my challenge for you. Go back and create a mirror universe where my hiring decisions are the opposite of what they normally would be and see what that decision tree looks like compared to the one that we start with. So go have some fun with that, and when you come back, we'll go to the next section and talk about some more machine learning techniques.